When we think about galaxies, we often picture them smashing into each other, with stars colliding in an intense fiery display. The term galaxy crash sounds dramatic, almost like a car crash in space. But the reality is quite different. Galaxies don't actually crash in the way we imagine. Galaxies are made up mostly of empty space. In fact, stars within galaxies are incredibly far apart from one another. Even in the densest parts of galaxies, the distances between stars are vast. So when galaxies collide, the stars themselves rarely ever collide. Instead, their gravitational pull interacts in ways that cause the galaxies to stretch, distort, and sometimes even merge together, but without direct star-to-star impact. For example, imagine two cities that stretch for miles in every direction. If they were to merge, the buildings wouldn't crash into one another, because there's so much space between them. The cities might change. Maybe a few streets would shift, but the buildings themselves stay mostly untouched. This is what happens when galaxies collide. It is more like a slow-motion dance, with stars staying in their own orbits, while the galaxies themselves twist and merge. A good example of this is the collision of the Andromeda galaxy and our Milky Way. They're on a path that will eventually lead them to merge in about 4 billion years. This sounds like a catastrophic event, but it will be a gradual process. The stars in both galaxies will pass by each other without any significant collisions. The real impact will be felt in the structure of the galaxies themselves, with the gravitational forces causing them to reshape over time. The stars, on the other hand, will mostly continue on their paths, largely unaffected by the merger. One might wonder why there isn't much star-to-star collision, given the force at play in these galactic encounters. The answer lies in how galaxies are spread out. Even when galaxies come into close contact, the empty space between their stars means that most of the stars won't have a chance to interact. Think about two large crowds walking towards each other in a vast open field. Though the people might get closer and overlap in the middle, the likelihood of them bumping into each other is low because of all the space in between them. The same idea applies to galaxies. In these galactic encounters, the real drama comes from the way the galaxies affect each other through their gravity. As the galaxies approach, their mutual gravity begins to pull them towards each other. This results in a stretching effect, causing the galaxies to distort. We can observe this in the form of long, stretched out arms of stars and gas, and sometimes whole new regions of star formation. This is due to the disruption of the galaxy's normal structure, and it can give the illusion of chaos. However, no stars themselves are actually crashing into one another. This gradual merging process isn't limited to just the Milky Way and Andromeda. Galaxies collide all the time across the universe, though most of these events are not easy to observe because they are far away or occur too slowly. The result of these collisions is often the creation of new, larger galaxies. Over time, smaller galaxies may be absorbed by larger ones, and the stars within them may be scattered or placed into new orbits. This process has happened many times throughout the history of the universe, and it will continue as galaxies evolve and grow. Another factor that contributes to the low chances of stars colliding is the movement of stars within a galaxy. Each star in a galaxy is moving along its own orbit. Even in a crowded part of a galaxy, stars are constantly moving, which makes it unlikely for them to meet head-on. Instead, their paths may pass by one another, but they don't stop to interact. Think of it like a busy highway with cars all moving in different directions. Though the cars are very close to each other, the chances of them colliding are slim because they're each traveling along their own paths. The sheer distance between stars and their constant movement means that even in the most dramatic galaxy mergers, the stars often avoid collision. There are some exceptions to this, of course. In rare cases, gas clouds within galaxies might collide leading to intense bursts of star formation. But even in these cases, it's the gas that's interacting, not the stars themselves. The gas is much less spread out than stars, so it has a higher chance of colliding, and when it does, it can lead to new stars being born. But these interactions still don't mean that stars themselves are crashing into each other. It's easy to assume that when galaxies meet, everything within them is in danger of colliding. But in reality, it's the galaxy's shapes, structures, and movements that are altered, not the individual stars. This makes the idea of galaxy crashes more of a fascinating cosmic event than a catastrophic one. The stars within these galaxies don't face immediate danger, even as their homes undergo massive transformations. Even with all this, the idea of galaxies colliding still captures the imagination. The thought of two massive collections of stars, gas, and dust merging into something entirely new is awe-inspiring. But the drama is not in the collisions of stars. It's in the reshaping of galaxies, the tug of war between their gravity, and the eventual creation of something even bigger and more complex. It's not the individual stars we should be concerned about. It's the transformation of the whole galaxy. In the end, galaxy collisions are some of the universe's most spectacular, yet peaceful events. They show us how gravity and time can slowly reshape everything without the destructive chaos we might expect. The stars themselves continue their orbits, while the galaxies themselves change. It's a slow process, one that happens on timescales that far exceed a human lifetime. And it's a reminder of how vast and empty space really is, even in the most crowded galaxies. When two galaxies approach each other, something powerful starts to happen. They pull on each other. This pull is caused by gravity. Every object with mass exerts a gravitational force, and galaxies, being made of billions of stars, have a lot of mass. So, when galaxies get close, their gravity begins to work on each other. This is not just a gentle tug, it's a strong pull that can stretch and distort the galaxies, changing their shapes. Think of it like two large balls floating through space. If they get close enough, their gravitational fields will start to affect one another. The closer they get, the stronger the pull. Now, imagine if these two balls are made of a soft, stretchy material. As they approach, their surfaces begin to stretch and warp, especially in the areas closest to each other. That's a simple way to picture what happens when galaxies interact. In a galaxy, stars are spaced far apart, so they usually don't collide with each other. But the gravity between two galaxies can pull the stars out of their regular paths. This tug of war between the galaxies causes them to stretch and twist, creating long arms of stars and gas that spiral outward. These distorted shapes are a clear sign that the gravity between the galaxies is at work. To see this in action, you only need to look at galaxies that have already collided or are on the verge of doing so. The Andromeda Galaxy and the Milky Way, for example, are on a path to collide in a few billion years. As they get closer, their mutual gravity will stretch and distort their shapes, even before they fully merge. The Milky Way, which is currently a disk-shaped galaxy, will begin to warp as Andromeda's gravity pulls on it. Over time, the two galaxies will eventually combine into a single larger galaxy, but not before their shapes change dramatically. When the galaxies pull on each other, they can stir up the gas and dust between the stars. This can lead to new stars forming. The compression of gas can cause it to heat up, which may lead to the birth of new stars in what's called a starburst. So, while the stars in the galaxies won't crash into each other, the gas clouds that fill the space between them can collide and trigger new activity. One of the most dramatic examples of gravitational interaction comes from the merger of the Whirlpool Galaxy and its neighbor, a smaller galaxy called NGC 5195. The larger galaxy's gravity has stretched the smaller one, creating a noticeable distortion. The arms of the Whirlpool galaxy have been warped and twisted by the pull of NGC 5195. The smaller galaxy has been pulled out of its original shape, and both galaxies now share a new gravitational relationship. Gravity also has a way of pulling objects into orbits. When galaxies collide, their stars and other components begin to move in new directions. Some stars get pulled into the gravitational field of the larger galaxy, while others might be flung out into space. These stars will no longer follow their original paths. Instead, they will be captured by the gravitational forces of the new merged galaxy or sent into entirely new regions of space. In a way, it's like what happens when you spin two marbles close to each other on a smooth surface. As they get closer, the marbles begin to roll in different directions. One marble may be pulled towards the other and eventually end up orbiting it. This is a simplified version of what happens to stars when galaxies interact. Over millions of years, the gravitational forces can cause entire sections of galaxies to change. For example, galaxies can become more elliptical rather than spiral, shaped after a merger. The distinct arms that spiral out from a galaxy might smooth out or become stretched into long lines. These changes happen gradually as the galaxies interact. The more massive galaxy tends to dominate the smaller one, pulling it apart over time. In some cases, galaxies can pass by each other without merging. This is called a flyby. Even though the galaxies don't merge in a flyby, their gravitational forces still pull on each other, causing them to distort temporarily. After the flyby, the galaxies might return to their original shapes, but sometimes they're left with permanent changes. Their paths through space are altered, and their structure may never be the same. Think of it like two cars passing close by each other on a road. If they get too close, their gravity can affect each other. One car might be slightly pushed off its original path. Even though the cars don't collide, they've still been changed by their close encounter. Gravity doesn't only affect galaxies when they are in direct contact, it works over vast distances, slowly pulling galaxies toward each other. If two galaxies are far apart, but moving toward one another, their gravity will still affect the way they move. It might take billions of years for them to collide, but during that time, they will still be influenced by each other's gravity. This long-range gravitational effect is important because it can explain how galaxies are pulled toward larger clusters. Even if galaxies are far away from each other, the gravity from a large cluster of galaxies can slowly pull them in, eventually leading to collisions or mergers. Galaxies are always in motion. They can spin around their centers, drift through space, and of course interact with other galaxies. But it's the gravitational pull that keeps them in line even when they're far apart. This is why the interactions between galaxies are so important. Their gravity shapes the way they move, grow, and evolve. In some ways, gravity is like the invisible force that ties everything together in the universe. It's responsible for keeping stars in their orbits around galaxies, and it's also the force that causes galaxies to move and collide. The gravitational forces at play in these interactions are powerful enough to reshape galaxies, to stir gas clouds, and trigger star formation, and to send stars on new paths across space. When we look at galaxies colliding or merging, we are seeing the results of this gravitational pull. It's a force that doesn't need to touch the stars to have an enormous impact on their worlds. When galaxies collide, something remarkable happens. The intense gravitational forces at play squeeze the gas clouds that fill the space between the stars. This compression can trigger a burst of star formation, turning quiet regions into hotbeds of new stars. It's like a storm rolling through a forest, causing trees to bend and crack, and creating space for new growth. In the case of galaxies, the storm is the gravitational interaction, and the new growth is the birth of stars. Gas clouds in galaxies are made up mostly of hydrogen, and this gas is the raw material for stars. Normally, these clouds float through the galaxy, relatively stable and unchanging. But when galaxies collide, their gravitational forces cause these clouds to compress. As the gas is squeezed, it becomes denser and the pressure increases. This compression can cause the gas to collapse, and when it does, it can trigger the formation of new stars. This process is called starburst, and it's a sudden, intense period of star creation that occurs when galaxies interact. Imagine two large, soft balls filled with air, pushing toward each other. As the balls come together, the pressure increases where they meet, causing the air inside to compress. If the pressure is high enough, the air might suddenly burst out, creating a forceful explosion. In galaxies, this compression isn't quite an explosion, but it's a similar idea. As the gas clouds are compressed by the galaxy's gravity, the pressure forces the gas to collapse, sparking the birth of new stars. This kind of star formation can happen on a massive scale. In some galactic collisions, the gas clouds can collapse so quickly that thousands of new stars are born in just a few million years. This is a much faster rate of star formation compared to what's typical in galaxies, where stars are usually born over millions or even billions of years. The interaction between the galaxies speeds things up, leading to a surge of star creation. One well-known example of this phenomenon is the collision between two galaxies called the antennae galaxies. These galaxies, located about 60 million light-years away, are in the midst of merging. As they collide, their gas clouds are compressed, and the result is a huge increase in star formation. In fact, the antennae galaxies are one of the most active sites of star formation ever observed. The collision has triggered the birth of tens of thousands of new stars, and astronomers continue to study the event to understand how such large-scale star formation can happen so quickly. This surge in star formation can also change the way a galaxy looks. As new stars are born, they can brighten up the area where the collision is happening, creating intense regions of light. These regions, often called starburst regions, are packed with young, hot stars. The bright light from these stars can make the galaxy appear more colorful, especially in the infrared spectrum, where the heat from young stars is most noticeable. Another example is the collision between the galaxies M82 and M84. M82, often called the Cigar Galaxy, has a central area where star formation is happening at a rate hundreds of times faster than in the Milky Way. The collision between M82 and M84 has caused their gas clouds to interact, triggering a huge burst of new stars. The result is a galaxy that is much more active than it was before, with areas of intense star creation lighting up its center. This is one of the clearest signs that galactic collisions can significantly boost the rate of star formation. The gas clouds that trigger this burst of star formation are mostly made of hydrogen, but they can also contain heavier elements like helium and dust. The process of compressing and collapsing these gas clouds not only makes them denser, but also raises the temperature. As the gas heats up, it begins to glow, which helps astronomers spot regions of intense star formation. These glowing regions are often visible in many wavelengths of light, from radio waves to visible light to infrared. The pressure from the gravitational forces can also trigger the creation of new types of stars. For example, massive stars, which are much larger and hotter than the average star, often form in starburst regions. These stars burn through their fuel quickly and end their lives in spectacular supernova explosions. When a supernova occurs, it can send shockwaves through the surrounding gas, compressing it even further and triggering the formation of even more stars. This creates a cycle where the death of one star leads to the birth of more stars, fueled by the intense gravitational forces at play during the collision. The increase in star formation doesn't just affect the galaxy's appearances, it also changes their overall structure. As the gas clouds collide and compress, they can cause the galaxies to rearrange themselves. This can lead to the creation of new features, such as long streams of stars or gas that extend out from the main body of the galaxy. These features, often called tidal tails, are a direct result of the gravitational forces at play during the collision. In some cases, the galaxies can even form new shapes altogether, such as elliptical galaxies, after the gas clouds settle down and the star formation slows. While the star formation rate may surge during a galactic collision, it doesn't last forever. Eventually, the gas that fuels the star formation runs out or gets used up. Once the intense period of star creation slows down, the galaxies begin to settle into their new merged shape. The starburst phase is just a temporary event in the larger life cycle of a galaxy. But it can be one of the most dramatic moments in a galaxy's history. The surge in star formation is one of the most striking effects of galaxy collisions. While the stars themselves don't usually collide, the gas between them can be compressed so much by the gravitational forces that it leads to the creation of new stars. This process is one of the reasons why galactic collisions are so fascinating to astronomers. They offer a rare opportunity to observe how galaxies evolve and change, and how new stars are born under extreme conditions. As galaxies collide, they don't just change shape, they give birth to new generations of stars that will continue to shine long after the collision is over. Every large galaxy, including the Milky Way, likely has a supermassive black hole at its center. These black holes are incredibly dense, pulling in everything around them, including light. When two galaxies collide, their supermassive black holes can also come close to each other. Over time, the gravity of these black holes might bring them together, leading to a process that is both fascinating and complex. The merger of these black holes could result in an even larger black hole at the center of the new merged galaxy. To understand what happens during a galaxy collision, it helps to think about how black holes work. A supermassive black hole is millions or even billions of times more massive than the Sun. While the black hole itself is small in size compared to the entire galaxy, its gravity is so strong that it can pull in stars, gas, and other objects from the galaxy around it. The black hole sits at the very center of the galaxy, and everything in the galaxy revolves around it. In many ways, it is the anchor of the galaxy's structure. When two galaxies begin to collide, their black holes are drawn together by the gravitational forces of the merging galaxies. At first, the black holes might be millions of light years apart, but over time, they will move closer, drawn together by their mutual gravity. As the galaxies continue to interact and eventually merge, their black holes will also spiral toward each other. This process takes a long time, but eventually, the two black holes can merge into a single, even larger black hole. Imagine two whirlpools in a stream. Each whirlpool pulls in nearby water, and over time the two whirlpools get closer and closer. Eventually, they merge into one larger whirlpool, with a stronger pull than either had before. The same thing happens with black holes. As they get closer, their gravitational pull strengthens, and they spiral toward each other until they combine into one larger black hole. This merging process is incredibly violent and energetic. As the black holes get closer, they cause waves of energy to spread through space. These waves are called gravitational waves. Gravitational waves are ripples in space. Time, the very fabric of the universe. When two black holes merge, they create powerful gravitational waves that can be detected even billions of light years away. In fact, the first detection of gravitational waves by scientists in 2015 came from the merger of two black holes, proving that this process is not just theoretical, but something that actually happens in the universe. When black holes merge, they don't just combine their masses. The energy released during the process is enormous. In some cases, This energy can briefly outshine the combined light of all the stars in the galaxies involved. This burst of energy is often referred to as a black hole merger event. While this event is brief, it can be an incredibly powerful source of light and radiation shining across the universe. However, because black holes themselves do not emit light, this energy comes from the surrounding matter being pulled into the black hole, heating up as it falls in. As the black holes merge, the new, larger black hole that forms is often much more powerful than the two original black holes. It will have a stronger gravitational pull and will likely continue to grow by pulling in more nearby matter, including gas, dust, and even stars from the surrounding galaxy. Over time, the newly formed black hole will settle down into its new position at the center of the merged galaxy, and the energy from the merger will subside. One well-known example of this type of interaction is found in the galaxy NGC 6240. This galaxy has two supermassive black holes at its center, and evidence suggests that they are in the process of merging. The collision of these black holes is still ongoing, but eventually they will combine into a single, even larger black hole. The process has already caused a surge in the amount of energy released from the galaxy, and the merger of these black holes could be one of the most significant events in the galaxy's future. The merging of black holes can also affect the galaxies around them. For example, when the black holes come together, their gravitational forces can stir up the gas in the galaxy, causing more stars to form or sending gas and stars flying into space. This disruption can alter the structure of the galaxy itself, making it more elliptical or changing the way the stars move within it. The merger of black holes is not just about the black holes themselves. It's also about how their interactions affect the entire galaxy. It's important to note that black hole mergers are not the same as regular star collisions. When two stars collide, they can end in an explosion like a supernova, but with black holes, the process is quieter in some ways. There's no explosion of light or sound. Instead, the merger creates ripples in space, time that travel outward at the speed of light, carrying information about the black holes and their interaction. These ripples are detected by sensitive instruments like LIGO, which is designed to pick up gravitational waves. Even though the idea of black holes merging sounds dramatic, the reality is that these events happen over billions of years. The galaxies themselves might collide over the course of millions of years, but the actual merging of their black holes takes even longer. This process is so slow that we can't observe the black holes merging in real time. However, by studying galaxies that are in the process of merging, scientists can learn a lot about how black holes interact and grow over time. The eventual merging of black holes may be one of the most significant events in the universe. The larger black hole that forms from this interaction will have the power to influence its galaxy for billions of years to come. The newly formed black hole could continue to grow by pulling in more matter, and its gravitational pull could alter the orbits of stars in its galaxy. Over time, the galaxy will settle into a new shape, influenced by the forces from the black hole at its center. The merging of black holes is just one part of the larger story of galaxy collisions. As galaxies interact, their stars, gas, and even their black holes are all pulled into a complex dance. While the stars in the galaxies may not collide with each other, the gravitational forces between the black holes are incredibly powerful, leading to dramatic changes in the galaxies over time. When two galaxies collide, the outcome depends on a few factors like the size and speed of the gala. When two galaxies collide, the gravitational forces between them can have a surprising effect on their structure. Instead of simply merging into one, the galaxies can be stretched out, forming long, narrow streams of stars and gas. These streams are called tidal tails, or tidal streams, and they are one of the most striking features seen in galaxy collisions. Imagine two rubber bands being pulled toward each other. As the bands get closer, the forces between them cause them to stretch, and in some cases, the rubber bands might even snap, creating long, thin strands. This is a rough way to think about what happens when galaxies collide. As the galaxies get closer, their stars and gas clouds are stretched out by their mutual gravitational pull, forming these long, trailing streams. The process begins when two galaxies pass close enough for their gravity to start interacting. The gravity from one galaxy pulls on the other, and vice versa. This pull causes the galaxies to stretch, with the stars and gas being tugged outward. As the galaxies continue to move through each other, the material between them becomes more and more stretched, eventually forming long, thin streams of stars and gas that trail behind the galaxies. These streams can stretch for hundreds of thousands of light years, far beyond the main body of the galaxies. One of the most famous examples of tidal tails is the antennae galaxies. These two galaxies are in the process of merging, but the gravitational interaction between them has already started to stretch them into long, thin shapes. The result is a pair of galaxies with large tidal tails that curve out from their centers. These tails are made up of stars, gas, and dust, all of which have been pulled out by the gravity of the two colliding galaxies. The antennae galaxies provide a perfect example of how a galaxy collision can lead to the formation of tidal tails. Another well-known example is the galaxy NGC 4038, 4039, also known as the antennae. This galaxy pair is also in the process of merging, and the tidal tails formed by their collision are clearly visible. These streams stretch far away from the main bodies of the galaxies and are full of stars and gas. They are a direct result of the gravitational forces pulling the two galaxies apart. As the galaxies continue to interact, the tidal tails will grow longer and more stretched, and the galaxies will eventually merge into a single, larger galaxy. Tidal tails are not just a result of the galaxy's collision. They also tell us a lot about the galaxies themselves. The material in these streams comes from the stars, gas, and dust that are in the galaxies. As the galaxies pass by each other, the gravitational forces can strip away some of this material, pulling it into the tidal tails. The gas and dust in these tails can eventually collapse to form new stars, making the tidal tails not just a product of the collision, but also a place where new stars are born. These tidal tails also show the complex ways that galaxies interact with each other. When galaxies collide, it's not just a simple merging of two masses. The gravitational forces between the galaxies can distort their shapes, pulling on different parts of the galaxies in different ways. This creates regions where the stars and gas are compressed, and others where they are stretched out, forming the tidal tails. The way these tails form depends on many factors, like the size of the galaxies, their relative speeds, and the angle at which they collide. In some cases, the tidal tails can stretch so far that they begin to break apart. This happens when the gravitational forces are too strong, or when the galaxies pass by each other at a high speed. The material in the tidal tails can be pulled away from the main galaxy and dispersed into space. Over time, the tidal tails may become less distinct as the stars and gas spread out, but the gravitational interaction that created them remains a powerful force, shaping the future of the galaxies involved. Not all galaxies that collide form tidal tails. In some cases, the galaxies might pass by each other, without stretching into long streams of stars and gas. This happens when the galaxies are not close enough for their gravity to have such a strong effect on each other. However, when tidal tails do form, they provide a visible reminder of the dramatic forces at work during a galaxy collision. One of the interesting things about tidal tails is that they can tell us about the past history of a galaxy. By studying the stars and gas in these streams, astronomers can learn about the galaxies that form them. The stars in the tidal tails often have different properties from the stars in the main body of the galaxy. For example, they might be older or younger, depending on how long ago the collision happened. The gas in the tidal tails can also show how the galaxies interacted, how much material was stripped away, and how new stars are being formed in the streams. The study of tidal tails is an important part of understanding galaxy collisions and mergers. When galaxies interact, they don't just create dramatic visual effects, like the stretching of stars and gas. These interactions can also lead to the formation of new stars, the rearranging of gas, and the shaping of new galaxies. Tidal tails are one of the clearest signs of the power of gravity at work in the universe, pulling entire galaxies apart and shaping the stars and gas in ways that are hard to imagine. Tidal streams, which are similar to tidal tails, are another product of galaxy collisions. While tidal tails are long, narrow streams of material that trail behind the galaxies, tidal streams are the remnants of a galaxy's outer parts that have been pulled away by the gravity of a nearby galaxy. These streams are often less dense than tidal tails and can stretch across even larger areas. They are also made of stars and gas that have been separated from the main galaxy, but they don't always have the clear, defined shape of tidal tails. Tidal tails and streams are natural products of the gravitational forces that act during galaxy collisions. When galaxies interact, they don't simply pass through each other. Their gravity stretches, distorts, and pulls them apart, creating long, narrow streams of stars and gas. These streams, called tidal tails or tidal streams, can stretch for vast distances, and they provide a visible record of the forces at work during the collision. Tidal tails also play a role in the birth of new stars, showing how galaxy collisions can be a source of new growth in the universe. When galaxies collide, the stars within them don't just stay where they are. Their orbits, which are usually stable, can shift dramatically. This happens because the gravitational forces from the collision cause the stars to experience significant changes in their positions and velocities. Essentially, the stars get caught in a new complex dance where their paths through space are altered, and they may end up in completely different locations within the newly merged galaxy. To understand how this works, imagine two spinning plates on a table, each filled with marbles. As the plates collide, the marbles on the edges might be flung outward or pulled inward, while the ones near the center may start spinning in new directions. The plates themselves continue to spin, but the marbles inside them have changed their paths because of the forces acting on them. This is somewhat like what happens to stars when galaxies collide. Their motion is affected by the gravity from the other galaxy, and their orbits are disrupted. Before a collision, the stars in a galaxy generally follow regular, predictable orbits. These orbits are influenced by the gravity of the galaxy's center, where the supermassive black hole resides. Most stars stay in their own regions, moving around the center in fairly steady paths. But when another galaxy enters the scene, its gravity starts to tug on the stars, shifting their orbits and causing them to move in new directions. For example, when two galaxies pass by each other, the gravitational interaction can push some stars toward the center of the galaxy, while others are pulled outward. This happens because the gravitational forces between the galaxies are not uniform. In some areas, the forces might be strong enough to compress the orbits of stars, pushing them closer together. In other areas, the forces might stretch out the orbits, causing the stars to move further away from the center. The result is a chaotic mix of new orbits for the stars, with some ending up much closer to the galactic center and others being sent to the outer edges of the galaxy. A clear example of this process is seen in the collision between the galaxies NGC 4038 and NGC 4039, known as the antennae galaxies. These galaxies are merging, and as their stars interact with each other, their orbits are being altered. The gravitational forces are strong enough to pull stars from the outer regions of the galaxies toward the center, while others are flung outward into the tidal tails, long streams of stars and gas that stretch far from the merging galaxies. As the collision continues, the stars in both galaxies are rearranged, with their orbits changing in ways that reflect the new gravitational influences. In some cases, stars that were once part of one galaxy might be pulled into the other galaxy. This happens when the gravitational forces are strong enough to overcome the star's original orbits. These stars can end up in new positions, orbiting the center of the merged galaxy. Some might even be ejected entirely, flung out of the galaxy and into intergalactic space. This can happen if the stars experience a gravitational slingshot, where the forces from the collision give them enough speed to escape the galaxy's gravity entirely. The shifts in stellar orbits are not just random. They depend on several factors, including the size and speed of the galaxies involved, the angle at which they collide, and the distribution of mass in each galaxy. When two galaxies collide head-on, the stars in both galaxies are likely to experience stronger gravitational forces, leading to more dramatic changes in their orbits. If the galaxies collide at an angle, the effects on their stars might be less intense, but the gravitational interaction can still cause significant orbital shifts. As these changes occur, the stars within the galaxies can start to cluster in new patterns. For example, in the aftermath of a galactic collision, a galaxy might develop a new, more elliptical shape, with stars distributed more evenly throughout the galaxy. This happens because the gravitational interactions during the collision push the stars into new, more chaotic orbits. In some cases, a galaxy's spiral arms might disappear entirely, replaced by a more rounded or diffuse structure. The stars themselves might no longer be in well-defined orbits, but instead move in more random patterns due to the disordered forces at play. The stars near the center of the galaxy are also affected by the collision, but in a different way. In many galaxies, the center contains a supermassive black hole, which has a strong gravitational influence. During a collision, the movement of stars near the center can become more chaotic as they interact with the gravitational forces of the merging galaxies. In some cases, the stars near the black hole can be pulled into the center, increasing the density of stars around the black hole. This can lead to the formation of a new, more active galactic nucleus. In other cases, the central black hole might grow as it pulls in more material from the surrounding stars and gas. While the stars in the colliding galaxies are changing their orbits, the process of star formation can also be affected. When gas clouds within the galaxies collide, the compression from the gravitational forces can cause the gas to heat up and collapse, triggering the formation of new stars. These newly formed stars can also experience shifts in their orbits as they are pulled by the changing gravity around them. This adds another layer of complexity to the overall changes in a galaxy's structure following a collision. The rearrangement of stars in a galaxy is not limited to just one event. As the galaxies continue to interact over time, the gravitational forces between them will keep altering the stars' orbits, causing ongoing changes to the galaxy's structure over millions or even billions of years. This process can lead to the complete transformation of a galaxy, changing not just the positions of the stars, but the very shape of the galaxy itself. A good example of this can be seen in the galaxies that are in the process of merging into elliptical galaxies. These types of galaxies have stars that are more randomly distributed rather than following the well-organized orbits seen in spiral galaxies. The stars in elliptical galaxies are often the result of earlier mergers, where the gravitational forces disrupted the orbits of the original stars. Over time, the stars settle into new, more random orbits, resulting in the smooth, rounded appearance of elliptical galaxies. The shifting of stars' orbits during a galactic collision is a key part of what makes galaxy mergers so fascinating. These shifts don't just change the stars' positions, they also influence the overall evolution of the galaxies. The stars in a galaxy can end up in completely new locations, and the new orbits they follow can affect everything from star formation to the galaxy's shape. As galaxies merge and their stars are rearranged, The end result is often a galaxy that looks very different from what it was before the collision began. The stars may have moved, but the galaxy itself has evolved, shaped by the powerful gravitational forces at play. When two galaxies collide, the effects are not just felt by the stars. The gas clouds within the galaxies also interact, and these interactions can trigger powerful events. As the gas clouds crash into each other, shock waves are created. These shock waves compress the gas, and under the right conditions, this compression can lead to bursts of new star formation. This process is a dramatic part of galaxy collisions and can lead to the birth of many new stars in a short amount of time. Imagine two clouds in the sky moving toward each other. When they collide, the pressure between them causes the air to condense, and new cloud formations begin to form. In space, the gas clouds within galaxies behave in a similar way. The gas is mostly made of hydrogen, the building block for stars. This compression causes the gas to heat up and collapse, triggering the formation of new stars. The process starts with the galaxies getting close enough that their gas clouds interact. As the collision progresses, the gas within each galaxy is funneled toward the point of impact, where it is squeezed together. When this happens, the density of the gas increases and the pressure rises. In certain regions, this causes the gas to collapse, and as the gas becomes more compact, it begins to form stars. This is what is known as a starburst event. In a starburst, the rate of star formation increases dramatically, sometimes by hundreds of times more than the normal rate in a non-colliding galaxy. A well-known example of this is the collision between the galaxies NGC 4038 and NGC 4039, often called the antennae galaxies. These two galaxies are in the process of merging, and as their gas clouds collide, they are creating intense bursts of new stars. The collision has caused parts of the gas to compress to the point that new stars are being born at an accelerated rate. In fact, the antennae galaxies are one of the most active sites of star formation ever observed. The collision of the gas clouds has made the region incredibly bright in infrared light, which is a sign of star formation happening at a rapid pace. The shock waves created by these gas collisions are not just a simple matter of the gas coming together. The compression of the gas can cause it to heat up significantly. As the gas heats up, it begins to glow. And this is part of what makes star-forming regions visible in the universe. The shock waves trigger the collapse of smaller gas clouds, which eventually become new stars. These newly formed stars are often massive, young, and bright, and they burn through their fuel much faster than older stars. As a result, they create large amounts of energy, which further drives the process of star formation. This process can also result in the formation of new star clusters. Star clusters are groups of stars that form together from the same gas cloud. In the case of galaxy collisions, the gas clouds that collide often contain enough material to create multiple new star clusters. These clusters are often tightly packed with young stars, and they can be a spectacular sight in the aftermath of a galactic collision. Another example is the merging of the galaxies M82 and M84. M82 is a starburst galaxy, meaning that it has experienced a surge of star formation. This burst is largely due to the interaction with its neighboring galaxy, M84. The gravitational forces between the two galaxies have pushed gas clouds in M82 together, causing them to collide and compress, resulting in a new burst of star formation. The resulting stars are so bright that they make M82 one of the most intense star-forming galaxies in the universe. The collision between the galaxies has also caused the gas to be funneled into the center of M82, further fueling the star formation. Not all gas collisions lead to star formation. In some cases, the gas clouds might not have enough material to trigger the collapse needed to form stars. The density and temperature of the gas play a major role in whether or not stars will form. However, when conditions are right, These gas collisions can result in the birth of a large number of stars in a short period of time. The gas clouds themselves may eventually be depleted, but the starburst event can leave behind a new generation of stars that will continue to evolve in the merged galaxy. When galaxies collide, and their gas clouds collide as well, the effects can last for millions of years. Star formation can continue long after the initial collision, as the gas that has been compressed continues to collapse and form stars. The process is gradual, and the galaxies themselves are not completely transformed overnight. Instead, the star formation builds up over time, with each wave of compressed gas leading to the birth of new stars. Over the course of billions of years, these events can change the very nature of the galaxy, leading to a completely new structure. In some cases, these bursts of star formation can significantly alter the appearance of the galaxy. After the collision, the galaxy may no longer resemble its original shape. The center might become much more crowded with stars, and the outer regions might become more diffuse. The new stars born from the collision may cluster in new patterns, reshaping the overall structure of the galaxy. Over time, the galaxy will settle into a new form, often an elliptical shape, with the stars dispersed more evenly throughout. The impact of gas collisions in galaxy mergers also extends to the environment around the galaxies. When large amounts of gas are compressed and new stars are born, the energy created by these stars can send shock waves through the surrounding space. This energy can cause the surrounding gas to heat up and spread out, sometimes causing the galaxy's surroundings to become more active. In some cases, the energy from the new stars can even expel gas from the galaxy entirely, leaving behind a starburst galaxy with a much less dense outer region. The collision of gas clouds within colliding galaxies is one of the key drivers of new star formation in the universe. It is a process that takes place over vast timescales, with the effects of the collision gradually altering the structure of the galaxy. As the gas clouds compress and collide, they trigger the formation of new stars, often in large bursts. These bursts can lead to the creation of star clusters and the reshaping of the galaxy itself. The energy and shock waves generated by the collision play a critical role in fueling these processes, driving the creation of new stars and changing the galaxy's overall structure in the aftermath of the collision. When galaxies collide, the result is often a dramatic transformation in their shape. Galaxies that once had distinct, organized forms, such as spiral galaxies, can lose their structure and evolve into something new. This happens because of the intense gravitational forces involved in the collision. These forces stretch, pull, and compress the galaxies, which leads to a reshaping of their overall structure. Take a spiral galaxy, for instance. Before a collision, a spiral galaxy has arms that twist outward from its center, creating a well-organized rotating disk. The stars in a spiral galaxy follow fairly regular orbits, and the galaxy looks like a flat, thin disk from the outside. But when another galaxy comes close, its gravity begins to interact with the stars and gas in the first galaxy. This gravitational pull distorts the spiral arms and can cause the stars to shift from their regular orbits. The result is a gradual loss of the galaxy's original shape. Imagine stretching a rubber band. If you pull on it too hard, it will no longer keep its circular shape. Instead, it will get longer, thinner, and distorted. The same thing happens when galaxies collide. As the galaxy's gravitational forces pull on each other, the stars and gas inside them are stretched, causing them to lose their distinct shape. The spiral arms of a galaxy might be pulled apart or merged into a smoother structure, turning the galaxy into something that looks more like an ellipse than a disk cone. Common outcome of galaxy collisions is the formation of elliptical galaxies. Elliptical galaxies are much more rounded and smoother than their spiral counterparts. The stars within an elliptical galaxy move in more random orbits rather than the organized rotations seen in spiral galaxies. When two spiral galaxies collide, Their gravitational interaction can cause the stars to scatter and the gas to compress or get redistributed. Over time, the galaxy's original spiral shape can become less defined, and the galaxy may become more spherical or elliptical in appearance. The result is a galaxy that lacks the familiar spiral arms, looking more like a ball of stars with a smooth, featureless surface. An example of this process can be seen in the merging of the galaxies NGC 4038 and NGC 4039, which are often referred to as the antennae galaxies. These two galaxies are in the process of colliding, and their interaction has already begun to distort their shape. The original spiral structure of both galaxies is becoming less clear, and the galaxies are starting to resemble more of an elliptical shape. As the collision continues, the galaxies will likely lose their spiral arms altogether, becoming a single, more rounded galaxy. Another classic example is the collision of the Milky Way with the Andromeda galaxy. Over the next few billion years, these two galaxies will collide and merge. Currently, the Milky Way is a spiral galaxy with distinct arms, while Andromeda also has a spiral shape. But after the collision, the combined galaxy will likely have a more elliptical shape. The stars in the two galaxies will be scattered by the gravitational forces of the merger, and the gas will be compressed or redistributed. The once distinct spiral arms will be gone, replaced by a smoother, more evenly spread structure. Not all galaxy collisions lead to the formation of elliptical galaxies, however. In some cases, galaxies may not lose their spiral shape completely. If the galaxies are smaller or their collision is less intense, they may merge in such a way that some spiral features are retained. However, the process of merging often leads to changes that reduce the clarity of the original structure. Even in cases where the spiral shape is maintained, the galaxy may become much larger and more chaotic, with stars following more random paths. In addition to transforming into elliptical shapes, galaxies can also develop entirely new and unusual forms as a result of collisions. For example, the gravitational forces of a galaxy merger might cause a galaxy to stretch out in strange ways, forming long tidal tails, which are streams of stars and gas that trail from the main body of the galaxy. These tidal tails form because of the immense gravitational pull during a collision, which stretches the galaxy's stars and gas, pulling them into long, narrow extensions. The result is a galaxy that may appear elongated or distorted, rather than maintaining a simple, smooth shape. An example of this is the case of the galaxy M82, often referred to as the cigar galaxy. M82 is a starburst galaxy, which means it is undergoing an intense period of star formation. The galaxy's elongated shape was caused by the gravitational interaction with a nearby galaxy. M84, the collision between the two galaxies, has pulled M82 out of its original shape, creating a long cigar-like appearance. The interaction between the galaxies has led to the gas in M82 being funneled toward its center, fueling a burst of star formation and altering the galaxy's overall structure. In some cases, a galaxy might not simply lose its spiral arms or become elliptical. It might become more irregular, with a shape that is difficult to classify. These irregular galaxies are often the result of a more chaotic collision, where the gravitational forces create unpredictable changes in the galaxy's structure. Irregular galaxies are usually smaller than spiral or elliptical galaxies and often appear as clumpy, disordered collections of stars. Their appearance may result from a recent collision or merger, where the galaxy has not had time to settle into a more stable form. The process of a galaxy shape changing during a collision is often slow and happens over millions or billions of years. The first signs of a shape transformation might appear as a slight distortion of the galaxy's arms or a subtle increase in the overall size. As the galaxies continue to merge, the distortion becomes more pronounced. Eventually, the galaxy might lose its original structure entirely, transforming into something unrecognizable. Over time, the merged galaxy might settle into a new form, with the stars following new orbits and the gas redistributing. Even in cases where the new shape is elliptical, the galaxy will continue to evolve, with ongoing star formation in the center and outer regions. The transformation of a galaxy's shape is a key part of the life cycle of galaxies, marking a major change in their structure and the way they evolve over time. While it might seem that galaxy collisions are destructive, the changes they cause in the shape of the galaxies can be seen as a natural part of the cosmic process. These transformations are driven by the immense gravitational forces at play and lead to the creation of new, more massive galaxies. Over billions of years, these collisions and shape changes contribute to the ongoing evolution of galaxies, reshaping the universe in ways we are just beginning to understand. As galaxies collide, their centers, home to supermassive black holes, slowly begin to merge in the final stages of the collision. These black holes are often millions or even billions of times more massive than the Sun, and they play a crucial role in shaping the dynamics of the merging galaxies. When these black holes come close enough, they may eventually spiral toward each other and merge. This process is not only dramatic, but it also leads to the release of an intense amount of energy that can have significant effects on the surrounding galaxy. At the start of a galaxy collision, the two galaxies may pass through each other without much immediate effect on their centers. The gravitational pull from the galaxies distorts their shapes, and gas and stars move around. But the supermassive black holes at their centers often remain far apart. Over time, however, the interaction between the galaxies causes the centers to get closer, and the black holes are gradually drawn toward each other. This happens because the black hole's gravity pulls them together, and as they move closer, their mutual gravitational attraction grows stronger. Eventually, the black holes can become so close that they begin to spiral toward each other, orbiting around a common center of mass. This process, called in-spiral, is slow and can take millions to billions of years. During this phase, the black holes are still far enough apart that they don't directly merge, but their gravitational influence on the surrounding gas and stars is already significant. The gas around the black holes may be compressed and heated as the black holes draw closer, causing intense radiation to be emitted. This can lead to bright bursts of energy, known as active galactic nuclei, and which are often visible across great distances. As the black holes continue to spiral inward, the energy they release becomes even more extreme. At the moment of final merger, the two black holes merge into one supermassive black hole. This process releases an enormous amount of energy in the form of gravitational waves, ripples in space, time that travel outward at the speed of light. These waves carry information about the masses of the black holes and their spin rates, and they can be detected by sensitive instruments like LIGO, even if the event occurs billions of light years away. The merger of these black holes is one of the most energetic events in the universe. The release of energy can cause a burst of light visible across vast distances. The newly formed black hole will be more massive than the two original black holes combined, and it will continue to grow as it pulls in more material from its surroundings. This process can also cause the galaxy's structure to change. The release of energy during the black hole merger can blow away surrounding gas, leaving the galaxy with less material to form stars. This can lead to a slowdown in star formation and a change in the overall appearance of the galaxy. An example of this process can be seen in the merging of two galaxies that is already underway in the center of the Virgo cluster. The galaxies in this cluster are close enough that their supermassive black holes will eventually merge. In this case, the merger will lead to the formation of a new, more massive black hole at the center of the resulting galaxy. The merger will also likely cause a burst of energy which will be detectable by astronomers. Another well-known example is the collision between the Milky Way and the Andromeda galaxy. These two galaxies are on a collision course, and in about 4 billion years, their supermassive black holes will likely merge. As they spiral toward each other, the black holes will release immense amounts of energy, affecting the surrounding gas and stars. The resulting merged black hole will be far more powerful than the two individual black holes, and the energy released during the process will reshape the central region of the newly formed galaxy. During these mergers, the gravitational waves produced by the black hole merger are one of the most important signals that astronomers look for. These waves carry information about the black holes involved, including their masses and spins. When two black holes merge, they send out gravitational waves that ripple through spacetime, and these waves can be detected by observatories like LIGO and Virgo. The detection of these waves from a black hole merger allows scientists to study events that are otherwise invisible, providing crucial information about how galaxies evolve and how supermassive black holes interact. The energy released during a supermassive black hole merger can also affect the larger galaxy in ways that are still being studied. The intense radiation produced by the merger can heat up the surrounding gas, causing it to become less dense and slowing down the rate of new star formation. In some cases, the energy can blow gas and dust out of the galaxy altogether, leaving behind a galaxy that has fewer stars and less material for future star formation. This can change the entire evolution of the galaxy, turning it from a star-forming active galaxy into a more passive one. The newly formed black hole that results from the merger will continue to grow by pulling in gas and stars from the surrounding galaxy. Over time, the black hole may even grow large enough to become the dominant force in the center of the galaxy, controlling the movement of stars and gas. This can lead to the formation of a more stable elliptical galaxy, with stars following more random orbits around the central black hole. In some cases, the merger of two black holes can also trigger a surge of star formation in the galaxy. The energy released during the merger can compress the surrounding gas, causing it to collapse and form new stars. This can lead to a temporary burst of star formation, which is known as a starburst. However, this surge in star formation is typically short-lived, and over time, the galaxy will settle into a new, quieter state. The merger of supermassive black holes is a dramatic event in the life of a galaxy, but it is just one part of the larger process of galaxy collisions and mergers. The collision of two galaxies can lead to a complete transformation of the galaxies involved, changing their shape, their star formation rates, and their overall structure. The merging of their black holes is the final step in this process, and it has a profound impact on the galaxy's future. As the black holes merge, they release an enormous amount of energy, reshape the central region of the galaxy, and pave the way for the galaxy's continued evolution. The process of merging black holes is one of the most energetic events in the universe, and it provides valuable insights into the forces that shape galaxies and the universe itself. When galaxies collide, the gas and dust that make up most of their material are squeezed together by the immense gravitational forces at play. This compression triggers a dramatic change in the way stars form. Normally, stars are born in the more stable environments of gas clouds scattered throughout a galaxy. But when these clouds are compressed, they collapse under pressure, causing an explosion of new star formation. This surge is called a starburst, and it leads to regions of intense stellar activity known as starburst regions. Think of it like pressing a sponge filled with water. When you squeeze the sponge, the water inside becomes more concentrated, and it pushes out of the sponge. In the case of galaxies, the compression of gas clouds during a collision causes the gas to collapse in on itself, increasing its density. As the gas collapses, it heats up, and the pressure forces it to form new stars much faster than usual. This process is incredibly efficient at creating new stars, and the result is a burst of star formation that can outpace the normal rate of star creation in a galaxy by hundreds of times. An example of this process can be seen in the antennae galaxies, where two galaxies are merging. The collision between the two galaxies has caused their gas clouds to compress, triggering a massive surge in star formation. The starburst regions in the antennae galaxies are some of the most active star-forming areas known. The gas that was once scattered throughout the galaxies has been funneled into these regions, where it has collapsed to form new, hot, young stars. These stars burn bright, and their light helps fuel the intense activity in the region. The stars formed in starburst regions tend to be large, bright, and short-lived. These stars burn through their fuel quickly, emitting a tremendous amount of energy. Because they are so massive and bright, they stand out against the background of the galaxy. This sudden burst of light is often visible in the infrared spectrum, where the heat from these new stars can be detected. The energy from these stars also has an impact on the surrounding gas. The intense radiation can heat the gas to very high temperatures, pushing it outward and creating winds of gas that blow through the galaxy. Another example of increased stellar activity during a galaxy collision can be seen in the merging galaxies M82 and M84. M82 is undergoing a massive starburst as a result of its interaction with the nearby M84. The compression of gas in M82 has created a long cigar-shaped galaxy with intense star formation in its center. The new stars in M82 are formed at a rate far higher than in a typical galaxy, and they emit an enormous amount of light, which has made M82 one of the most luminous galaxies known. The starburst in M82 is a direct result of the gravitational forces from the collision, which have funneled gas into the galaxy's center, sparking a rapid rate of star formation. In addition to creating bright new stars, the increased stellar activity during a starburst can also lead to the formation of star clusters. Star clusters are groups of stars that form from the same gas cloud, and they tend to be tightly packed together. During a starburst, large numbers of stars can form in clusters, and these clusters are often some of the most dense regions in the galaxy. Some of the most spectacular star clusters have been observed in galaxies that are undergoing starbursts, and they can contain hundreds or even thousands of young stars packed into a small area. The starburst regions created during galaxy collisions can also have lasting effects on the galaxies themselves. The energy from the newly formed stars can heat up the surrounding gas, causing it to expand and disperse. This can create winds of gas that blow away the materials surrounding the galaxy, stripping away parts of the gas that would normally be used for future star formation. Over time, this can cause the rate of star formation in the galaxy to slow down, as the galaxy runs out of material to create new stars. In some cases, the energy from the starburst can even trigger the formation of supernovae. Supernovae are massive explosions that occur when certain types of stars reach the end of their life cycle. The intense radiation and pressure created during a starburst can cause the gas in the galaxy to collapse, triggering the formation of new stars, some of which may eventually explode as supernovae. These explosions release vast amounts of energy and send shockwaves through the surrounding gas, which can further trigger star formation in nearby regions. The starburst activity can also alter the galaxy's appearance. Galaxies that are undergoing intense star formation often appear brighter and more colorful than galaxies that are not. The bright, young stars formed during a starburst give the galaxy a characteristic glow, especially in the infrared wavelengths, where the heat from these stars is most visible. Even though starbursts are temporary events, they can leave lasting marks on the galaxies that undergo them. Once the gas used for star formation is depleted or blown away, the galaxy may return to a more stable state, with star formation rates that are closer to what is normal for a typical galaxy. However, the stars created during the starburst will continue to evolve, and their impact on the galaxy's future evolution can be significant. The increased stellar activity during a galaxy collision is one of the most fascinating aspects of these events. The compression of gas, the formation of new stars, and the resulting bursts of energy can change the entire nature of the galaxy. These events lead to the creation of new stars, the alteration of the galaxy's structure, and the formation of star clusters and supernovae that continue to shape the galaxy's evolution long after the initial collision. The intensity of these bursts can be seen across great distances, allowing astronomers to observe the powerful effects of galaxy collisions and the immense forces at play. When two galaxies collide, the gas clouds within them don't just compress and form new stars. The interaction between these gas clouds also creates shock waves, powerful waves of pressure that ripple through space. These shock waves can have a dramatic effect, triggering supernovae, which are the explosive deaths of massive stars. The shock waves from these gas cloud collisions create the perfect conditions for stars to go out in violent bursts of energy, releasing vast amounts of light and material into space. Imagine a pressure wave moving through water when you drop a stone in a pond. As the wave travels outward, it can stir up the water around it, causing ripples and changes. In space, the shock waves created during galaxy collisions work similarly. As gas clouds collide, the compression causes the gas to become denser and hotter. This sudden increase in pressure and temperature creates shock waves that travel through the gas. These shock waves not only help to trigger new star formation, but can also push the stars to the edge of their life cycles, leading some to explode as supernovae. When a massive star dies, it can no longer hold up against the pressure of its own gravity. As the star's fuel is exhausted, the core collapses and the star explodes in a supernova. The explosion sends shock waves through the surrounding gas, and the energy released in the process is immense. These shock waves from supernovae can trigger further explosions and cause the surrounding gas to compress even more, creating a chain reaction that can lead to the formation of more stars. Essentially, the death of one star can help give birth to new ones, continuing the cycle of stellar creation and destruction. In a galaxy collision, shock waves created by the colliding gas clouds can trigger supernovae by compressing gas clouds to the point where they collapse, forming new stars. These new stars are often massive and short-lived. When these stars reach the end of their lives, they go supernova, adding more shock waves to the already intense environment. This process can continue for millions of years, with multiple generations of stars forming and dying, each explosion contributing to the overall activity of the galaxy. One example of this can be seen in the collision of the antennae galaxies. These galaxies are merging, and the interaction between their gas clouds has created shock waves that compress the gas and fuel bursts of star formation. In turn, some of the stars formed in these regions are destined to become massive stars that will eventually die in supernova explosions. The shock waves created by these explosions will add to the pressure in the surrounding gas clouds, pushing the cycle of star formation and death forward. The intense activity in the antennae galaxies has made them one of the brightest examples of starburst galaxies, where the birth and death of stars occur at an accelerated pace. Another example is the galaxy M82, which is undergoing a starburst due to its interaction with the nearby galaxy M84. The gas in M82 has been compressed by the collision, and as a result, stars are forming at a much higher rate than in a typical galaxy. Many of these new stars are large and unstable, and they will eventually explode as supernovae. The shock waves from these explosions help to continue the process of compressing the gas in the galaxy, creating the perfect conditions for more stars to form. The cycle of star formation and supernova explosions in M82 is one of the key reasons the galaxy is so active and luminous. Shock waves from supernovae can also have other effects on the galaxy. For example, when a supernova explodes, it releases a tremendous amount of energy and material into space. This can push gas and dust out of the galaxy or cause it to heat up, preventing further star formation in certain regions. Over time, the material from the supernova can mix with the surrounding gas, enriching it with heavy elements that are created during the explosion. These heavy elements are important for the formation of planets and life, and the spread of these materials into the galaxy helps to shape the future of the galaxy. The interaction between gas clouds and the shock waves that follow are a key part of the process that drives the evolution of galaxies. During a collision, the gas is compressed and heated, triggering a surge in star formation. This is followed by the deaths of some of the newly formed stars in supernova explosions. The energy from these explosions creates new shock waves, which in turn compress more gas, leading to even more star formation. The cycle continues, with stars being born and dying, and each event shaping the future of the galaxy. Over time, this process can alter the structure of the galaxy itself. The intense stellar activity can cause the galaxy to lose its original shape, with stars being scattered and gas being pushed out. In some cases, the galaxy may even lose so much gas that its star formation slows down or stops altogether. The shock waves from supernovae can be a contributing factor in this slowdown, as they heat the gas and prevent it from cooling down enough to form new stars. However, in galaxies where shock waves and supernovae are particularly intense, the cycle of star formation and destruction can continue for billions of years. The shock waves from gas cloud collisions and supernovae are not just a local phenomenon. They can also affect the larger environment around the galaxy. The energy released during a supernova can travel far beyond the galaxy, affecting other nearby galaxies or the intergalactic medium. In some cases, the shock waves can trigger star formation in other regions of space, causing new generations of stars to form in places far from the original collision. This shows how the effects of a galaxy collision can ripple out across the universe, influencing the creation of new stars and the evolution of distant galaxies. The process of shock waves and supernovae in galaxy collisions is a powerful force in shaping the universe. The compression of gas clouds, the birth of new stars, and the subsequent supernova explosions create a cycle of stellar activity that continues to drive the evolution of galaxies. These events, while violent and destructive, are also creative, leading to the formation of new stars, the spread of heavy elements, and the continual reshaping of galaxies across cosmic time. When two galaxies collide, one of the most dramatic events that can occur is the merging of their supermassive black holes. These black holes, which reside at the centers of galaxies, are millions or even billions of times more massive than the Sun. As the black holes get closer and eventually merge, the result is an intense burst of activity. The merging black holes begin to accrete material, mostly gas, dust, and stars. And this process leads to the formation of an active galactic nucleus, or AGN. This new structure emits powerful radiation, making the galaxy much brighter and more energetic than it was before the merger. Imagine two whirlpools in a river, each pulling in water from the surrounding area. As they get closer, their currents become stronger, and the water in between them begins to swirl faster. When the whirlpools finally merge, the water funnels into a single larger vortex. In the case of black holes, the gravitational pull from each one draws material toward the center. As the black holes spiral toward each other, they pull in more and more gas, creating a swirling disk of material. The energy generated by this process is enormous, and it is released in the form of radiation across many wavelengths, including X-rays and visible light. Before the black holes merge, they will be locked in an intense gravitational dance, pulling on each other's material. This interaction causes a lot of friction in the gas around them, which heats up to incredibly high temperatures. The gas spirals toward the black holes in a structure called an accretion disk. This disk is made up of gas and dust that is being pulled in by the black hole's gravity. As the gas gets closer to the black hole, it speeds up and heats up, emitting light and radiation in the process. The closer the gas gets, the more energy it radiates. This radiation is a sign of the intense activity taking place around the black holes. Once the black holes merge, the resulting singularity is even more massive and powerful. The newly formed black hole continues to pull in material from the accretion disk and surrounding space. This results in the formation of an active galactic nucleus, where the energy output is incredibly high. AGNs are often the brightest parts of galaxies, outshining the combined light of all the stars in the galaxy. The energy is released as radiation that can be observed across vast distances, making AGNs some of the most powerful and energetic phenomena in the universe. A prime example of this kind of activity can be found in the merging of two galaxies, NGC 6240. This galaxy has two supermassive black holes at its center, and as they spiral closer together, they create an intense region of radiation. The energy from this process heats up the surrounding gas, causing the galaxy to glow brightly. The radiation coming from this active galactic nucleus is powerful enough to be seen from Earth, even though NGC 6240 is over 400 million light years away. Another example is the merger between the Milky Way and the Andromeda galaxy, which is set to happen in about 4 billion years. The two galaxies will eventually collide, and their supermassive black holes will merge. As this happens, the newly formed black hole at the center will create an AGN, producing intense radiation as it accretes more material. The energy generated during this merger will likely be far greater than anything we currently observe in our galaxy. In fact, the new AGN may temporarily outshine the rest of the galaxy, becoming one of the brightest objects in the universe. The process of accretion, the pulling in of gas and dust, during a black hole merger is not just a matter of gathering material. The energy released during this phase has a profound effect on the surrounding galaxy. As the black hole pulls in material, it can generate strong jets of high-energy particles that shoot out from the poles of the black hole. These jets travel at nearly the speed of light, and their energy can extend far beyond the galaxy, affecting the intergalactic medium. The jets from an AGN can push gas out of the galaxy, slowing down the rate of star formation and affecting the galaxy's evolution. In some cases, the formation of an AGN can even lead to the expulsion of gas from the galaxy. This is because the radiation and jets produced by the black hole can be so powerful that they push the surrounding gas outward. This process is called feedback, and it can have a lasting impact on the galaxy's star formation rate. When gas is expelled, there is less material left to form new stars, which can slow down or even halt star formation in the galaxy. In the long run, this can change the way the galaxy evolves, transforming it into a more passive, older galaxy with fewer new stars being born. The energy emitted by an AGN is not just a temporary event. The process of accretion and the resulting radiation can last for billions of years, shaping the evolution of the galaxy over time. The black hole at the center of the galaxy continues to pull in material, generating radiation and jets. These black hole-driven phenomena can significantly influence the galaxy's shape, star formation, and overall behavior. Over time, the energy from the AGN can also impact the larger region around the galaxy, affecting the intergalactic medium and possibly triggering star formation in neighboring galaxies. The merging of supermassive black holes into an AGN is one of the most powerful and energetic events in the universe. The radiation released during the process can be observed across vast distances, allowing astronomers to study the activity taking place around these black holes. The energy produced by the merging black holes has a profound effect on the galaxy, influencing its star formation, structure, and evolution. As black holes merge and form AGNs, they become key drivers in shaping the future of galaxies, affecting their dynamics and helping to explain some of the most energetic processes in the universe. When galaxies collide, the process is far slower than it might seem. From a human perspective, it can be hard to grasp just how much time is involved. The merging of two galaxies, especially large ones, can take tens of billions of years to complete. In fact, most of the action in a galactic collision unfolds over such a long span of time that it's barely noticeable during a human lifetime. To truly understand what happens during a galaxy collision, you have to think in terms of cosmic timescales, far longer than anything we typically experience on Earth. Consider two galaxies such as the Milky Way and Andromeda. These two galaxies are on a collision course and will eventually merge. But this event isn't something that will happen overnight, or even within a few million years. The actual merging of the galaxies won't take place for about 4 billion years. Before they fully merge, the galaxies will interact in many different ways, stretching, distorting, and pulling on each other. But these processes happen very gradually. Over millions of years, the galaxies will pass through each other multiple times, each time causing more disruption and change. However, even by the time the galaxies have passed through one another, their final merger may still be millions of years away. One reason for the slow pace of galaxy mergers is the vast amount of space between the stars within galaxies. Although a galaxy can contain billions or even trillions of stars, the stars themselves are incredibly far apart. Even in the densest parts of a galaxy, the distances between individual stars are so large that direct star-to-star collisions are highly unlikely. Instead, the collision mostly affects the gas and dust between the stars. The gravitational pull between the galaxies causes their shapes to distort, stretches their arms, and triggers bursts of star formation. But this doesn't result in immediate, dramatic changes. Instead, the process unfolds over billions of years. For example, when the Milky Way and Andromeda begin their final merger, they will pass through each other multiple times over millions of years. As they do, their gas clouds will collide, triggering star formation and distorting the galaxy's shapes. But the stars themselves will mostly avoid direct collisions. Instead of colliding in a dramatic fashion, the stars will follow altered paths, moving in response to the gravitational tug of their companion galaxy. This gradual movement will cause the galaxies to eventually settle into a new, more stable configuration. But that process will take billions of years. Even when the galaxies fully merge, the resulting structure will not immediately resemble the original galaxies. Over time, the stars will adjust to their new orbits, and the combined system will likely take on a new, more elliptical shape. However, the final stages of the merger will take an incredibly long time, and the galaxies will continue to evolve as their stars adjust to the new gravitational landscape. Another factor that contributes to the slow nature of galactic collisions is the fact that galaxies don't often collide head-on. Most collisions happen at an angle, and this means that the interaction between the two galaxies is less direct. The galaxies might graze each other, pulling on one another and stretching out their shapes, but the full direct collision, when the galaxies merge into one, will take much longer to unfold. These grazing interactions, which can stretch over millions of years, cause the stars to adjust their positions. But again, the actual process of merging is so slow that it can seem almost imperceptible on the timescale of a human lifetime. The pace of galaxy mergers can also be seen in the history of other galactic collisions that have already occurred. For example, the large elliptical galaxy M87 in the Virgo cluster has likely absorbed many smaller galaxies over billions of years. This process didn't happen quickly. Rather, it was a slow, gradual series of interactions that led to the merger of many smaller galaxies into a single, larger galaxy. The results of these slow mergers are clear in the smooth, featureless appearance of M87. The stars in M87 are spread out in a more random pattern compared to the well-organized spiral arms of a spiral galaxy. This is because the smaller galaxies that were absorbed into M87 gradually adjusted to the new gravitational forces over billions of years. Even as these mergers take place, they are far from being instantaneous events. The actual process of one galaxy being absorbed into another is spread out over an enormous timescale. During this time, the dynamics of the galaxies change significantly, but this shift happens so gradually that it's difficult to observe within a single human lifetime. Understanding the timescale of galaxy collisions also helps explain why we don't always see the immediate effects of these cosmic events. For instance, when galaxies collide, they often experience intense bursts of star formation in the areas where their gas clouds compress. While this star formation is an exciting event, it happens over a long period of time and doesn't just result in a sudden burst of new stars. Instead, the star formation happens gradually, and it can take millions of years before the full effects of the collision are visible. The stars born from these events might be short-lived, burning brightly for a few million years before dying in supernova explosions, which then send shock waves through the surrounding gas and dust, leading to the formation of even more stars. Similarly, when supermassive black holes at the centers of galaxies begin to merge, the process happens over an extended period of time. The black holes don't just collide instantly. Instead, they spiral toward each other over billions of years, with each orbit drawing them closer until they eventually merge. During this time, the black holes can release bursts of radiation as they accrete gas, creating an active galactic nucleus. And these AGNs are extremely bright and energetic, but they're the result of a slow process that takes a long time to unfold. Ultimately, the process of galactic mergers is a testament to the vast scale of time in the universe. While it may seem like something dramatic is happening in a galaxy collision, in reality, these events happen over such long periods that they're imperceptible on the scale of a human life. Even our own galaxy, the Milky Way, will collide with Andromeda. But that event is still billions of years away, and the actual merging process will stretch out across even more time. The slow pace of these cosmic events is a reminder of the immense timescales over which galaxies evolve, and how, on the cosmic level, what seems like a dramatic event is just another part of the ongoing evolution of the universe. When galaxies collide, the immense gravitational forces at play can have some surprising effects on the light that passes through them. One of the most fascinating outcomes is a phenomenon called gravitational lensing. As the galaxies interact, their gravity bends and distorts the path of light traveling through space. This bending effect can create some stunning and unusual visual distortions, allowing us to see distant objects in ways we otherwise wouldn't be able to. Gravitational lensing occurs because of the way mass affects light. According to Einstein's theory of general relativity, light travels in straight lines unless it is influenced by a massive object, such as a galaxy or a black hole. When light passes near a large mass, like a galaxy in the midst of a collision, the mass bends the light's path, much like how a glass lens bends light. This effect is similar to how a magnifying glass can focus light and make objects appear larger or distorted. In space, however, instead of magnifying a small object, gravitational lensing can bend light from faraway galaxies, stars, and other cosmic objects, making them appear stretched, distorted, or even duplicated. Imagine a distant star or galaxy behind two colliding galaxies. Normally, this distant object would appear as a tiny point-like source of light. But if the galaxies in the foreground are massive enough, their gravitational pull bends the light from the distant object, creating distorted shapes. In some cases, the light from the distant object might form arcs, rings, or even multiple images of the same object. These visual effects happen because the light is being bent in different ways, depending on how it passes through the gravitational field of the colliding galaxies. One known example of gravitational lensing can be seen in the Hubble Space Telescope's images of distant galaxies. In some cases, we can observe multiple images of a single distant galaxy that has been lensed by a massive galaxy in the foreground. The light from the distant galaxy is bent by the gravity of the foreground galaxy, making it appear as though there are several copies of the same galaxy in different parts of the sky. This happens when the foreground galaxy aligns just right with the distant object, creating a lens effect that distorts the light. The resulting images can look like arcs or rings, which are often called Einstein rings. During a galaxy collision, the gravitational pull of both galaxies acts on the light traveling through the space between them, and this can produce even more complex distortions. The more massive the colliding galaxies, the stronger their gravitational fields. This means that galaxies undergoing a collision, like the antennae galaxies, which are merging, are likely to produce some of the most striking gravitational lensing effects. The light from distant stars and galaxies behind these colliding galaxies is bent in ways that create intricate patterns, often revealing parts of the universe that would otherwise remain invisible. In some cases, the gravitational lensing effect can also reveal information about the mass and structure of the galaxies involved in the collision. The way light bends can tell astronomers how much mass is contained in the galaxies and how that mass is distributed. By studying the light from background objects that are lensed by a galaxy, scientists can gain insights into the galaxy's shape, the distribution of its stars, gas, and dark matter, and even how its gravitational field is interacting with the light from distant sources. This is particularly useful when studying galaxies that are far away and difficult to observe directly. The visual impact of gravitational lensing during galaxy collisions can be quite dramatic. In some cases, distant galaxies or clusters of galaxies may appear as distorted shapes, with their light stretched into long arcs, or even forming complete rings around the lensing galaxies. This effect, often seen in the collision of galaxy clusters, can make it look like the background galaxies are being magnified or stretched out, revealing features that would otherwise be impossible to detect. These cosmic distortions give us a glimpse into how the universe is shaped by the gravitational influence of massive objects. One striking example of gravitational lensing during galaxy collisions is seen in the images of the Bullet cluster, a pair of galaxy clusters that collided with each other. In this case, the gravitational lensing effect from the collision caused the light from more distant galaxies to be bent into multiple distorted images. The result is a dramatic view of the universe, where background galaxies appear as arcs and rings around the collision. These lensed images provide crucial information about the mass and structure of the galaxy clusters involved, helping scientists understand the distribution of dark matter, which doesn't emit light but can still exert gravitational forces. Another example comes from the collision of the galaxies NGC 4038 and NGC 4039, the antennae galaxies. As these galaxies interact, their massive gravitational fields distort the light coming from distant galaxies behind them. This creates complex patterns of light that are both visually striking and scientifically valuable. The gravitational lensing effects here allow astronomers to study not only the galaxies involved in the collision, but also the distant objects being lensed by the intense gravity. In some instances, gravitational lensing from a galaxy collision can also provide valuable clues about the dark matter surrounding the galaxies. Dark matter is an invisible form of matter that doesn't emit light, but its presence can be detected through its gravitational effects. By studying the way light bends around galaxies, scientists can learn more about how dark matter is distributed within these galaxies and how it affects the overall dynamics of the universe. Gravitational lensing is not just a curiosity. It provides a unique opportunity to study objects and phenomena in the universe. that would otherwise be too faint or distant to observe directly. The bending of light by massive galaxies in collision opens up new possibilities for exploring the cosmos. These visual effects, while captivating, are also powerful tools for astronomers, helping them uncover secrets about the mass, structure, and history of galaxies. As galaxies continue to collide across the universe, the lensing effects they create will continue to offer incredible insights. The resulting cosmic distortions are not only beautiful to observe, but they also deepen our understanding of the forces shaping the universe. Gravitational lensing during galaxy collisions provides a window into the invisible, revealing the power of gravity and the hidden structures of the universe in ways that would be impossible to achieve without these extraordinary cosmic events. When galaxies collide, the larger galaxy often ends up absorbing the smaller one in a process known as cosmic cannibalism. This happens because the gravitational forces at play during a galaxy collision are much stronger than the forces holding the smaller galaxy together. As the two galaxies interact, the smaller galaxy is gradually pulled apart, and its stars, gas, and dust are drawn into the larger galaxy. Over time, the smaller galaxy is consumed, its original structure lost, as it becomes part of the larger galaxy. Imagine two creatures in the wild, where one is much larger than the other. When they encounter each other, the larger one might overpower the smaller one, slowly consuming it. The same thing happens in the vastness of space. Galaxies, which are made of billions of stars, can be thought of as these cosmic creatures, and when they collide, the gravitational forces become the driving factor in the interaction. The smaller galaxy doesn't simply crash into the larger one and break apart instantly. Instead, the gravitational pull of the larger galaxy gradually tears the smaller galaxy apart, stretching it into long streams of stars and gas that are absorbed into the larger galaxy. A well-known example of this process can be observed with the Milky Way and its satellite galaxies. The Milky Way is already in the process of absorbing several smaller galaxies. One such galaxy is the Sagittarius Dwarf Elliptical Galaxy, which has been gradually torn apart by the Milky Way's gravity. Over time, the stars and gas in the Sagittarius galaxy have been pulled into the Milky Way, adding to its mass. While the Sagittarius galaxy still exists, much of its original structure has been lost, and its remnants continue to be absorbed into the Milky Way. This process of cosmic cannibalism doesn't happen quickly. It unfolds over millions or even billions of years. The smaller galaxy is not instantly destroyed. Instead, it gets stretched out by the gravitational pull of the larger galaxy. This stretching creates long, thin tidal tails, streams of stars and gas that trail behind the smaller galaxy as it is pulled apart. The stars within the smaller galaxy are gradually incorporated into the larger galaxy's structure. Some of the stars may even end up in the central region of the larger galaxy, adding to the star population there. One of the most striking examples of cosmic cannibalism is the collision between the Andromeda galaxy and its satellite galaxies. Andromeda, which is much larger than the smaller galaxies orbiting it, has already absorbed several of these smaller galaxies over time. The larger mass of Andromeda's gravity has stripped away stars, gas, and dust from its satellites, adding them to its own structure. Andromeda is in the process of absorbing the M32 galaxy, and this is just one example of how the larger galaxy continues to grow by consuming smaller galaxies. As a galaxy is cannibalized, it loses its original shape. The smaller galaxy's spiral arms or elliptical structure begin to dissolve as the stars are pulled out and scattered. In some cases, the remnants of the smaller galaxy can still be traced by looking at the tidal tails left behind, long streams of stars that were once part of the galaxy. These tidal tails often stretch out into the surrounding space, visible even billions of light years away. These streams can help astronomers trace the path of a smaller galaxy that has been consumed by a larger one, revealing how galaxies evolve over time. Not all galaxies get completely absorbed during a collision. In some cases, a smaller galaxy may survive the interaction, but it can still be significantly altered. Some of the gas and stars may be stripped away, leaving the galaxy in a more disrupted state. The gravitational pull from the larger galaxy may change the orbits of the remaining stars, altering the shape of the galaxy and causing it to become more elliptical or irregular. Even when a smaller galaxy survives, its original structure and identity may be lost as it becomes a part of a larger galactic system. This process of cosmic cannibalism is a natural part of galaxy evolution. Over billions of years, galaxies grow by merging with and consuming smaller galaxies. This process leads to the formation of larger galaxies, like our Milky Way, which have absorbed many smaller galaxies over time. In fact, most large galaxies, including the Milky Way, are the result of multiple mergers and the gradual incorporation of smaller galaxies. The effects of cosmic cannibalism extend beyond just the galaxies themselves. As the smaller galaxy is consumed, the stars within it may begin to interact with the stars of the larger galaxy. Some of the stars may be flung out into intergalactic space, while others may be pulled into the central black hole of the larger galaxy. This process can also trigger bursts of star formation in the larger galaxy, as the gas from the smaller galaxy is compressed and heated by the gravitational forces. The collision and consumption of galaxies can, in fact, create new generations of stars, especially in regions where the gas has been compressed by the interaction. While the smaller galaxy is being consumed, the energy released by the gravitational interaction can also cause other effects. The tidal forces can heat up the gas, causing it to emit X-rays and other forms of radiation. In some cases, the material being pulled into the larger galaxy can form an active galactic nucleus, where a supermassive black hole consumes the gas and produces intense radiation. This process can make the larger galaxy more energetic and brighter, especially in the central regions. Cosmic cannibalism is a slow process, but its effects are profound. Over time, the smaller galaxy is completely absorbed, leaving behind little more than a scattered remnant. The larger galaxy grows in size and mass, while its structure may become more elliptical or irregular. The stars and gas that were once part of the smaller galaxy are redistributed, and the original identity of the smaller galaxy is lost. In some cases, the remnants of the consumed galaxy can still be seen in the form of tidal tails or disrupted stellar populations. But these are just the echoes of what once was. As galaxies continue to collide and merge, cosmic cannibalism will remain a key driver in the evolution of the universe. Larger galaxies will continue to consume smaller ones, gradually growing in size and complexity. The effects of these interactions can be seen throughout the cosmos, with galaxies constantly merging and evolving. Cosmic cannibalism is a reminder of the immense forces at play in the universe, shaping galaxies and determining the structure of the cosmos over billions of years. When two galaxies collide, their effect isn't limited to just the stars and gas in the galaxies themselves. The galactic halo, the vast region of dark matter and stars that surrounds the visible part of a galaxy, can also be influenced by the collision. Each galaxy has its own dark matter halo, an invisible structure made up of dark matter, which exerts a gravitational pull on the galaxy and its contents. When galaxies merge, these halos don't simply stay separate. Instead, the dark matter halos of the merging galaxies may combine into one larger halo, reshaping the distribution of mass and affecting the overall structure of the new merged galaxy. To understand this, it helps to think about the invisible cloud surrounding a galaxy. Just as a galaxy is made up of stars, gas, and dust, it is also surrounded by dark matter that is invisible to our eyes, but can be detected through its gravitational effects. This dark matter is spread throughout the galactic halo and plays a crucial role in the galaxy's overall mass and gravitational pull. The dark matter in these halos doesn't interact with light the way regular matter does, but its gravitational influence is critical in shaping the galaxy. Now, when two galaxies collide, the gravitational forces between them are immense. The dark matter halos from both galaxies start to interact, and over time, they merge into a single larger halo. This process isn't immediate. It happens gradually as the galaxies move closer, pass through each other, and eventually combine into a single larger galaxy. Imagine two bubbles floating toward each other in the air. As they meet, their surfaces start to stretch and merge into a larger, more irregular shape. Similarly, as two galaxies collide, their dark matter halos stretch and overlap, gradually merging into one. This new, larger halo may have a different shape or density compared to the original halos, and it will exert a stronger gravitational pull on the newly formed galaxy. In practical terms, the merging of these halos can have important consequences. For one, the gravitational pull from the combined halo affects how the stars, gas, and other matter within the galaxy move. The stars in the new galaxy may follow new orbits, and the overall shape of the galaxy might change as a result. The merger of dark matter halos can also lead to the formation of a more massive galaxy, as the additional dark matter adds to the overall mass of the system. An example of how this process works can be seen in galaxy clusters. When smaller galaxies collide within a larger galaxy cluster, their dark matter halos merge into a single, more massive halo. This effect is part of the process that leads to the formation of galaxy clusters, where galaxies and their halos come together to form a massive gravitational structure. In these cases, the merging of halos is a key factor in the growth of the cluster as the total mass of the system increases. The merging of dark matter halos during a galactic collision can also affect the way galaxies behave after the merger. The new, larger dark matter halo might exert different gravitational forces on the galaxy's stars and gas, which can lead to changes in the galaxy's shape. For example, the galaxy might become more elliptical in appearance, with stars moving in more random orbits rather than following well-defined spiral arms. This happens because the gravitational pull from the larger dark matter halo can cause the stars to be redistributed in a more chaotic manner. Even though dark matter is invisible, the effects of its gravitational pull are very real. As dark matter halos merge, they shape the galaxy in significant ways. The stars and gas in the galaxy are influenced by the gravity of the combined halo, which can lead to changes in the galaxy's structure and behavior. Over time, this process can contribute to the formation of new galaxies with more irregular shapes, especially when the merger involves galaxies with very different sizes or masses. In some cases, the merging of dark matter halos can also lead to the creation of new regions of star formation. When the dark matter halos combine, they can cause the gas in the galaxy to be compressed, which can lead to the formation of new stars. This effect is particularly noticeable during the final stages of a galactic collision. When the gravitational forces are strongest, the combined halo can drive the gas toward the center of the galaxy, triggering a burst of star formation. This phenomenon can make the newly formed galaxy much brighter, as new stars are born in the process. The changes in the dark matter halo during a galactic collision also have long-term effects on the galaxy's evolution. Once the halos merge, the new gravitational structure will affect how the galaxy interacts with its environment. For example, the larger halo may make the galaxy more likely to merge with other nearby galaxies, as its stronger gravitational pull can draw in more matter. Additionally, the merger of halos can influence how the galaxy behaves in a larger galactic cluster. In these clusters, the combined gravitational influence of many dark matter halos helps shape the movement of galaxies within the cluster, leading to the formation of galaxy superclusters over cosmic time. One interesting aspect of this process is that the effects of merging dark matter halos can sometimes be observed indirectly. While dark matter itself cannot be seen, astronomers can detect its presence by looking at the way galaxies and their halos interact with light. For instance, when light from distant galaxies passes through the dark matter halo of a galaxy in the foreground, it can be bent by the gravity of the halo. This phenomenon, called gravitational lensing, is one way astronomers can study the distribution of dark matter. By analyzing how light is distorted, scientists can learn more about the mass and shape of the dark matter halo and how it changes during a galaxy collision. The merging of dark matter halos is a crucial part of galaxy evolution. As galaxies collide and their halos combine, the overall mass and gravitational influence of the system grow, leading to changes in the galaxy's shape, behavior, and interactions with other galaxies. The gravitational forces at play during these events have a lasting impact on the galaxy's future, shaping its structure and guiding its evolution for billions of years to come. This merging process is part of the larger cosmic dance of galaxies, where dark matter plays an essential role in the growth and development of the universe. When galaxies collide, one of the most important things that happens is the mixing of gas and dust. These materials, which are scattered throughout galaxies, are the building blocks for stars and planetary systems. As the galaxies interact, their gas and dust clouds collide and compress, creating the conditions necessary for the formation of new stars. This process not only leads to the creation of new stars, but can also trigger the formation of new planetary systems as the material clumps together. To understand how this works, imagine two large clouds of gas and dust slowly coming together. As they collide, the particles inside them are squeezed closer together. This compression increases the density of the gas, which causes it to heat up. The increase in pressure and temperature makes the gas more likely to collapse in on itself, and as it does, it forms dense regions. These dense regions are where stars begin to form. When enough gas and dust are compressed together, it can trigger the birth of a new star. Much like how a ball of gas and dust in space can eventually collapse to create a star, the process is similar to what happens in a star nursery, where new stars are born from dense regions of gas. When two galaxies collide, the gas and dust that were once scattered throughout the galaxies are funneled into more concentrated areas, where they begin to condense and collapse. As the gas gets denser, it heats up and the pressure increases, causing it to collapse even more. This collapse can lead to the birth of new stars, often in rapid bursts. These bursts of star formation are called starbursts, and they can produce a large number of stars in a short amount of time. One of the most famous examples of this is the collision between the antennae galaxies. These two galaxies are merging, and as their gas and dust clouds collide, they are creating intense regions of star formation. In fact, the rate of star formation in these galaxies is much higher than in normal galaxies. The gas from both galaxies is funneled into concentrated areas, where it collapses and forms new stars. Some of these stars are massive and short-lived, burning brightly for a few million years before they die in supernova explosions. The shock waves from these explosions then compress more gas, creating conditions for even more stars to form. The antennae galaxies are a prime example of how a collision can fuel a surge in star formation. As new stars form in these starburst regions, some of the gas and dust surrounding them may also begin to clump together in the same way. When gas and dust accumulate in a dense enough region, they can form planets, in the same way that stars are born from collapsing gas clouds. Planets can form from the material left over around a new star. The process of planet formation is complicated, but it generally starts with the gas and dust surrounding a newly formed star coming together to create larger objects, which then collide and merge to form planets. This process can take millions of years, but eventually the system can become stable, with planets orbiting the new star. This phenomenon of gas and dust mixing during a galaxy collision also means that the collisions can lead to the creation of entirely new planetary systems. As gas clouds from two merging galaxies collide, the material within them becomes more concentrated and starts to form stars. The leftover gas and dust around these new stars may begin to form protoplanetary disks, which are the early stages of planetary systems. These disks contain the building blocks for planets, moons, and other objects that will eventually become part of the new system. Some of the stars that are formed during a galaxy collision may eventually have planets forming around them, creating the potential for new planetary systems to emerge. Another example of this process can be seen in the merger between the Milky Way and its satellite galaxies. The Milky Way has already absorbed several smaller galaxies over the course of its history, and the collisions between these galaxies have contributed to the formation of new stars. The gas and dust clouds from these smaller galaxies have been funneled into the Milky Way, adding to the material available for star formation. Some of the stars that have been created during these mergers have planetary systems, and over time, the Milky Way has grown in size and complexity, partly due to the addition of material from these smaller galaxies, while the formation of new stars and planetary systems is an exciting result of galaxy collisions. The process also has other effects on the galaxies involved. As the gas and dust collide, the material can be heated and compressed to the point that it is expelled from the galaxy. This can happen when a supernova explosion or the radiation from new stars blows gas out of the galaxy. This expulsion of gas can stop star formation in some regions, as the galaxy loses the raw material needed to create new stars. However, this loss of gas also means that the galaxy can start to look different. Some of the new stars formed during the collision will burn out over time, and without new gas to replace them, the galaxy may eventually become less active. The merging of gas and dust during a galaxy collision is a critical part of how galaxies grow and evolve. As the material is compressed and heated, it leads to the formation of new stars and possibly planetary systems. These new stars contribute to the brightness and energy of the galaxy, and the new planets may eventually support life, though this is a much slower process. The collision also affects the overall structure of the galaxy. Some of the gas and dust may be expelled, altering the rate of star formation and the overall dynamics of the galaxy. Ultimately, the collision of galaxies is a dynamic and ongoing process, one that contributes to the ever-changing nature of the universe. When two galaxies collide, the gas and dust within them undergo dramatic changes. Some of these clouds of gas and dust get compressed by the immense gravitational forces at play, and as they condense, they can create conditions that are similar to what led to the formation of our own solar system. In the aftermath of a galactic collision, new solar systems can form from these regions of concentrated material, potentially giving birth to stars and planets that will go on to develop their own unique characteristics. Imagine two vast clouds of gas and dust drifting slowly through space. When they collide, the pressure causes the particles to come closer together. As the material in these clouds becomes denser, it starts to clump together, much like how a snowball gathers more snow as it rolls. This clumping is the first step toward star formation, and when the material reaches a certain density, the process speeds up. The gas heats up, and the gravitational forces pulling the particles together grow stronger, eventually leading to the collapse of the cloud. This collapse creates the conditions for a new star to form at the center, while the remaining material around it can form planets, moons, and other objects that make up a solar system. This process is not an immediate one. It takes millions of years for the gas and dust to condense into dense regions where stars and planets can form. However, in the chaos of a galactic collision, there are likely many regions where gas and dust are compressed enough to trigger this process. These new solar systems may not be exactly like our own, but they could be similar in many ways. with planets orbiting newly formed stars. For example, after the collision of two galaxies, the gas clouds within them would be funneled into more concentrated regions. These regions, now under much more pressure, would collapse and form stars. Some of these stars would form in clusters, where multiple stars are born from the same cloud of gas. As the gas in the region continues to collapse, some of the material would not fall directly into the star, but would instead remain in a disk around it. This disk is made up of gas and dust, and it is from this material that planets, moons, and other objects can form. This process of planet formation would unfold much like the way our own solar system came together billions of years ago. The material in the disk surrounding the star would slowly come together, with smaller particles colliding and sticking together. Over time, these smaller particles would form larger bodies, eventually leading to the creation of planets. Some of these planets might be similar to the rocky planets in our own solar system, while others might resemble the gas giants like Jupiter or Saturn. The potential for new solar systems to form in these regions of gas and dust offers a glimpse into how the universe continues to evolve after a galactic collision. One example of this process can be observed in star-forming regions like the Orion Nebula. Though not the direct result of a galaxy collision, the Orion Nebula is a stellar nursery where gas and dust are actively collapsing to form new stars and planetary systems. The conditions in this nebula are similar to those that would arise in the aftermath of a galactic collision, where the compression of gas and dust leads to the formation of stars and the planets around them. The regions where stars are born in a galaxy collision would be similar to these nebulae, but on a much larger scale, potentially creating multiple new solar systems at once. While it's difficult to directly observe the formation of new solar systems in the aftermath of a galactic collision, the evidence suggests that this process is common. As galaxies collide, their gas and dust clouds are not only compressed, but also stirred up, leading to increased star formation. Some of these stars will have planets, and in some cases, those planets may have conditions conducive to life, just as Earth does. The gas clouds in these regions are the raw material for planet formation, and the gravitational forces at play during the collision help push the material together to form stable solar systems. The collision of galaxies doesn't just affect the stars within them, it also has a profound impact on the potential for planet formation. As gas and dust get compressed and funneled into dense regions, the chances of new solar systems forming increase. The process of star and planet formation takes place over millions of years. But in the aftermath of a galactic collision, these processes are likely to be much more widespread, with many new systems emerging from the chaos. Some of the planets in these new solar systems might be in the habitable zone, the region around a star where conditions are right for liquid water to exist. These planets might have environments that are suitable for life, depending on factors like their size, distance from their star, and atmospheric conditions. While the possibility of life in these new systems remains speculative, the potential for planets with the right conditions to form is real. After all, the process of planetary formation in one solar system is the same process that gave rise to Earth and its life. The formation of new solar systems in the wake of galactic collisions is part of the ongoing cycle of creation in the universe. As galaxies merge and their gas and dust clouds collide, new stars and planets are born. These newly formed systems will go on to evolve over billions of years, just as our own solar system did. The potential for new life in these systems is still unknown, but the fact that new stars and planets are continuously being formed highlights the dynamic nature of the cosmos. In the grand scheme of the universe, galactic collisions are a natural part of the evolution of galaxies. These collisions push the raw materials necessary for star and planet formation together, creating the conditions for new solar systems to emerge. Though these processes take time, they are part of the ongoing story of cosmic growth and change, a story that has been unfolding for billions of years and will continue for billions more. As galaxies collide, the process is long and gradual. It can take billions of years, but eventually, the two galaxies will merge into one. During this time, stars, gas, and dust move around and mix, creating new structures and dynamics. The result is a more massive galaxy, typically forming a large elliptical shape. This new galaxy will have a different look and feel compared to the original galaxies that started the process. When galaxies collide, they don't merge all at once. The process is spread out over a very long time. First, the galaxies begin to interact through their gravitational forces, stretching each other out and pulling on their stars and gas. The stars themselves mostly avoid each other because of the vast distances between them. But the gas and dust within the galaxies collide and compress, sparking new star formation. Over time, the galaxies pass through each other several times, and as they do, their shapes begin to change. The gravitational forces cause the spiral arms of a galaxy to be stretched, and its stars are pulled into new orbits. Eventually, after multiple passes and interactions, the two galaxies will begin to merge into one larger galaxy. This merger typically results in a new, more massive galaxy that is often elliptical in shape. The spiral arms of the original galaxies disappear as the stars are redistributed into a more spherical or elliptical pattern. The stars in the new galaxy move in more random orbits, instead of following the organized paths they once had in their original galaxies. The result is a galaxy that looks smooth and rounded without the familiar spiral arms that many galaxies, like the Milky Way, have. One well-known example of this process is the future collision between the Milky Way and the Andromeda galaxy. These two galaxies are on a collision course, and in about 4 billion years, they will merge into one. The process will take billions of years, and the final result will likely be a much larger, more massive galaxy with an elliptical shape. The stars in both galaxies will be pulled into new orbits. As the gravitational forces of the two galaxies interact, the gas and dust clouds will be compressed and heated, triggering bursts of new star formation. But over time, the merger will create a new, more stable structure. The resulting galaxy will have a different appearance and dynamics compared to either the Milky Way or Andromeda. During the final stages of the merger, the gravitational forces will become even stronger, pulling the two galaxies closer together. At some point, the supermassive black holes at the centers of the galaxies will merge as well. This will release an enormous amount of energy in the form of gravitational waves, which can be detected by sensitive instruments. The merging black holes will also lead to the formation of a new, more powerful active galactic nucleus, agene at the center of the new galaxy, emitting intense radiation as the black holes accrete material. As the galaxies merge and their shapes change, some of the gas and stars from the original galaxies will be lost in the process. The gravitational forces can strip gas away from the galaxy, leaving behind stars that are redistributed into the new galaxy's structure. Some stars might be ejected from the galaxy entirely, flung into intergalactic space, while others might fall into the central black hole, contributing to the galaxy's growth. The end result of the collision will be a much larger and more massive galaxy, but its structure will be different. It will likely become more elliptical, with a more random distribution of stars. The original spiral arms of the galaxies will be gone, replaced by a more rounded shape. The new galaxy will have a different dynamic compared to the two galaxies that began the process. The rate of star formation will likely slow down over time, as the gas available for new stars is used up or expelled, and the galaxy will become more passive. However, the central regions will likely remain active for a long time, with the supermassive black hole at the center continuing to accrete material. This process of merging galaxies is a natural part of the life cycle of galaxies. Over billions of years, galaxies collide, merge, and reshape. Each time a galaxy merges with another, it grows larger and more massive. These mergers lead to the creation of new stars and planetary systems, as gas and dust are compressed and funneled into areas where star formation can take place. But over time, as the galaxies lose their gas, or use it up in bursts of star formation, the rate of new star formation slows, and the galaxy becomes a more stable, older system. As galaxies continue to collide and merge across the universe, the process of galactic evolution continues. Larger galaxies form from the merging of smaller ones, and each merger creates new stars, planetary systems, and dynamics. This gradual, slow process shapes the universe over billions of years, leading to the complex array of galaxies we see today. And though the collision of galaxies might seem violent and chaotic, it is part of a larger ongoing cycle that drives the formation of new galaxies and stars, reshaping the universe in the process.